Hey everybody, Dr. A here, and in this video we are going to be giving a brief introduction and background information on steel beam columns. So if you recall, a vertically oriented compression member is typically known as a column, okay? And so when we think of a pure compression member, we're thinking of a member that is almost exclusively supporting axial compressive loads. And if it's oriented in a vertical direction, we commonly call it a column. Now, on the other end, we have pure flexure members, which we commonly call beams. And, beams are typically oriented horizontally, right? A horizontally oriented pure flexure member is typically called a beam. But what we're going to be talking about is what's called a beam column, okay? So a beam column is pretty much exactly what it sounds like. A beam column is a member that is subjected to a certain degree of both axial compression and internal bending or flexure. Okay. These are very commonly seen in statically indeterminate systems. Okay. So beam columns are commonly seen in statically indeterminate systems. Okay. So that's the basic definition of a beam column. So again, a quick and easy diagram of a beam column may look like this. If you have some kind of member that, maybe it's pin connected on its ends somehow, and it's subject to significant axial compression, but you also have some kind of loading along the span such that loading along the span causes it to flex, you may get some kind of deformation diagram or elastic curve that looks like this. And this deformation here is being caused by a buckling effect due to the P1 axial compressive loads. And on top of that, you have this applied loading along the length of the member that's additionally causing it to flex, okay? And so you can see this take many forms. You could see, maybe a form of it like this, where we have, loads in compression here, and then you have a transverse load here, P, and it's causing this thing to both buckle due to the compressive axial loads and due to the transverse loading causing it to flex, okay? So when we think about beam columns, again, we're looking at two aspects that we may have investigated separately before. A buckling effect due to axial compression, and a flexure effect and a bending effect due to transverse loading causing flexure of the member, okay? So in general, we need to recall that we want the following in design. We want required strength over available strength to be what? To be less than or equal to unity, 1.1. So we'll put ... in design. Okay, so if you've taken, any kind of design class, steel design, concrete design, whatever, in general, we want the required strength divided by the available strength. We want that ratio to be less than 1. So what we always want is the available strength to be bigger than the required strength that you need for a member to be successful, basically. Okay, so let's give a quick general review of some previous knowledge, some prerequisite material. For pure compression members, like columns, we generally have dealt with PU over phi C Pn being less than or equal to 1.0 for LRFD, okay? And then similarly, for pure flexure members, we've dealt with Mu over phi B Mn being less than or equal to 1.0 for LRFD. So these two little inequalities are more specific versions of this required strength over available strength. So Pu and Mu represent required strengths, right? So let's make a note of this. Pu and Mu represent required, and in this case, LRFD factored axial and flexural strengths, respectively. Okay, and then of course, what are phi C Pn and phi B Mn? Well, these represent your available strength, your LRFD available strength with those corresponding resistance factors built in. So we'll make a note of that. We'll say phi C Pn and phi B Mn represent the, again, the available, the factored available axial and flexural. Let's see if I can spell that right. Strengths. Okay, so and if you remember phi C, specifically this phi C value is the LRFD resistance factor for axial compression when dealing with steel members, and then phi B is the LRFD resistance factor for bending when dealing with steel members. So that's for, again, that's for pure compression and pure flexure. Now, what happens when you have both of these occurring at the same time? What happens when you have a member subject to both compression and flexure? So let's make a note of that. That's where we start talking about this idea of a beam column, okay? So for a beam column supporting both axial compression and flexure, what do we have in terms of this, required to available strength ratio? What does it end up manifesting itself as? Well, we end up with Pu over phi C Pn plus Mu over phi B Mn must be less than or equal to 1.0. So that means that the superposition of these ratios, when you add these ratios together, because both effects are happening to this member together, when you add them together, they still must be less than or equal to 1. So this is, again, we'll make a note here for LRFD, and we sometimes call this type of relationship an interaction equation. So this is a general interaction formula. And the reason why we sometimes call it interaction, it's an interaction formula, is because we are looking at the interaction between the effect of axial compression and the effect of flexure on one particular member. Okay, so this is a general equation though. When we get into the more specifics of steel design and also concrete design, we see some coefficients kind of manifest themselves regarding these ratios. So this is just meant to be a general overview of the idea of what we're kind of stepping into in some later videos with steel beam columns. So that concludes this video.